This video is brought to you by mywayteaching.com.
In this part, let us study what is this triple point. Okay. See, the temperature of a substance remain constant during its change of state. We already know this. It will be in thermal equilibrium. So, a graph between temperature T and the pressure P of the substance, we call it as phase diagram or PT diagram. So, this is the graph between pressure as well as temperature. See, the following figure you can see in this particular figure, it shows the phase diagram of water and carbon dioxide. So the first is, this is phase diagram of water, and here the figure B, this is the phase diagram of carbon dioxide. So such a phase diagram, it divides the PT plane into a solid region, vapor region and the liquid region. So you can see solid, liquid and vapor. In this also solid region, liquid region and vapor region. The regions are separated by the curves such as sublimation curve and fusion curve as well as vaporization curve. Okay. The points on the sublimation curve represents the states in which solid and vapor phases coexist. And the point on the sublimation curve BO, it represents the states in which solid and vapor phases coexist. Similarly, on the fusion curve, it represents the states in which solid and liquid phase coexist. Okay. And points on the vaporization curve represents the state in which solid and liquid phase coexist. So the temperature and pressure at which the fusion curve, vaporization curve and even the sublimation curve meet and all the three phases of a substance coexist is called as triple point of the substance. Okay. The temperature, pressure at which all these three, that is fusion curve, you can see this is vapor, liquid and solid. When all these three they meet at a particular point, it which means all these three curves and are coexist, all these three phases of a substance coexist, we call that point as the triple point of the substance. For example, you can take the triple point of water. It is represented by the temperature 273.16 Kelvin, and in terms pressure it is 6.11 into 10 raised to minus 3 Pascal. Okay. The triple point of water is occurs at the temperature that is 273.16 Kelvin, and if you consider the pressure, then that is given by 6.11 into 10 raised to minus 3 Pascal. Okay. In this part, let us study about an important concept, that is latent heat. Okay, so we already learned that certain amount of heat energy is transport between the substance and its surroundings when it undergoes a change of state, isn't it? So the amount of heat per unit mass transferred during this change of state of the substance is called as latent heat of the substance for the substance. Latent heat of that particular substance. The amount of heat which is transferred per unit mass. You just consider unit mass during the change of state of the substance. We call it as latent heat of the substance. Okay, for example, if heat is added to a given quantity of ice at minus 10 degrees Celsius. Okay, if heat is added to a given quantity of substance at minus 10 degrees Celsius, then the temperature of ice increases until it reaches its melting point, that is 0 degrees Celsius, isn't it? At this temperature, the addition of more heat does not increase the temperature, but it causes the ice to melt, or you can say it changes its state. So once that entire ice melts, again if you add heat, then that will change the temperature of the water. That will, results in increasing the temperature of water. A similar situation occurs during liquid gas change of state at the boiling point. Adding more heat to the boiling water causes vaporization without increase in temperature, isn't it? So the heat required during a change of state, it depends upon the heat of transformation and the mass of the substance undergoing a change of state. So how much heat is required in during the change of state, that it depends upon the heat of transformation. It depends on 2 points. The first point is it depends on the heat of transformation, and even it depends on the mass of the substance, isn't it? So undergoing a change of state. Thus, if mass m of a substance undergoes a change from one state to the other, then the quantity of heat required is given by ml. Okay, L is equal to m by q, where L we call it as, yes, we call it as latent heat, and it is also a characteristic of the substance. And the SI unit of this latent heat is given by joule per kg, and the value of L depends on the pressure. its value is usually quoted at standard atmospheric pressure, which means the latent heat for a solid liquid state change is called as latent heat of fusion. Okay, the latent heat for solid liquid state change, the amount of heat per unit mass to change the state from solid to liquid. We call it as latent heat of fusion, which is represented by LF. And similarly, for a liquid to gas state, we call it as latent heat of vaporization. So these are often referred to as heat of fusion and heat of vaporization. Okay, you can see in this table the temperatures of the change of state and latent heats for various substances at 1 atmospheric pressure. So here it contains the latent heat value for some of the substances and even their freezing and boiling points. Isn't it? They have given the value for ethyl alcohol minus 144 is the melting point, and latent heat of fusion is 1 joule per kg boiling point, and latent heat of vaporization. And similarly, it is given for gold, lead, mercury, nitrogen, oxygen, and even it is given for water. The melting point is 0, latent heat of fusion is 3.33, and 100 degrees Celsius, as we all know, it's the boiling point, and latent heat of vaporization for water, it is given by 22.6 into 10 raised to 5 joule per kg. Okay. So this is the table which gives the details of all those latent heats of very important substances which is considered at 1 atmospheric pressure. In this particular graph, you can see it is a plot of temperature versus heat energy for a quantity of water. So temperature versus heat energy for a quantity of water, and you can see in this figure when heat is added or removed during a change of state, the temperature remains constant. So in this figure you can see that the slopes of the phase lines are not same, isn't it? You can see the slopes of the phase lines are not at all same, which indicates that the specific heats of various states are not equal. At different states, the amount of heat required is different. For water, the latent heat of fusion and vaporization are different. So the latent heat of fusion, it is given by 3.33 into 10 raised to 5 joule per kg. It is written here, isn't it? And the latent heat of vaporization, it is given by 22.6 into 10 raised to 5 joule per kg. If you convert in terms of kilocalorie, then it is 540 kilocalorie per kg. That is 3.33 into 10 raised to 5 joules of heat is needed to melt 1 kg of ice at 0 degrees Celsius. Okay, the meaning of this is this only. Okay, 3.33 into 10 raised to 5 joules of heat energy is required to melt 1 kg of ice at 0 degrees Celsius, and 22.6 into 10 raised to 5 joules of heat is needed to convert 1 kg of water from to convert 1 kg of water to steam at 100 degree Celsius. Okay, so steam at 100 degrees Celsius carries 22.6 into 10 raised to 5 joule per kg more heat than water at 100 degrees Celsius. This is why burns from steam are usually more serious than those from boiling water. Okay.